The universe is a crime scene filled with the corpses of dead stars. We are all familiar with the most famous ones, the black holes, the silent, passive killers that wait for evidence to fall into them. They get all the attention. But today, we are not performing an autopsy on a black hole. We are here to investigate the other corpse, the one that is infinitely smaller, far more violent, and actively homicidal. This is the story of the neutron star and its evil parasitic twin, the Magnetar. This is not a star. This is a zombie. It is a city-sized atomic nucleus weighing more than our sun, spinning hundreds of times a second. And if you got too close, it wouldn't just spaghettify you. It would rip the very atoms from your bones from 100,000 miles away. Today, we conduct the autopsy of the deadliest object in the universe.
Before we can examine the corpse, we must understand the death. Our victim was a massive star, at least 8, perhaps 20 times the mass of our sun. For millions of years, it lived a stable life, fusing hydrogen into helium, a balance between the inward crush of gravity and the outward explosion of fusion. But it was a glutton. It burned through its fuel at an incredible rate. As documented in the case of supernovae, the star's core became a frantic, layered factory. For 90% of its life, it fused hydrogen. When that ran out, gravity compressed the core, temperature soared, and it began fusing helium into carbon. Then carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. Iron. In stellar forensics, this is the murder weapon. It is the end of the line. Unlike all the elements before it, fusing iron does not release energy, it consumes it. In the heart of this giant star, a core of dead, ash-like iron began to grow. The outward pushing furnace went out. Gravity, the patient killer, finally won. When the iron core reached 1.4 times the mass of our sun, the Chandrasekhar limit, a catastrophic failure occurred. The core, once the size of the Earth, collapsed in on itself. In less than a second, the electrons and protons in that core, the very building blocks of matter, were crushed together. An electron was forced into a proton, creating a neutron and a neutrino. The core, in a fraction of a second, collapsed from 8,000 miles wide to just 12 miles wide. It had become a solid ball of pure neutrons. The rest of the star, billions of tons of gas, was now in free fall, collapsing inward at a quarter of the speed of light. It slammed into this new, impossibly hard neutron sphere and bounced. A shockwave of unimaginable power tore outward, blasting the star's outer layers into space in the glorious explosion we call a supernova. But we are not here to look at the explosion. We are here for the body it left behind.
What is left is the neutron star. It is perhaps the most misnamed object in the sky. It is not a star. It is the collapsed nucleus of a dead one, a stellar corpse. Let's begin the external examination. The specimen is small. It is only about 12 miles or 20 kilometers across. You could drive around its equator in under an hour. But its mass
is staggering. This 12-mile sphere contains the mass of 1.5 of our suns. This is the densest object in the universe that is not a black hole. The popular analogy is a sugar cube. A single sugar cube of neutron star material would weigh 100 million tons. A thimbleful would weigh as much as all 7.8 billion humans on Earth combined. Its atoms are not 99.9% empty space like ours. Its atoms have no empty space. It is one giant, city-sized atomic nucleus. Because of this density, the surface gravity is 100 billion times stronger than Earth's. If you were to drop a gummy bear from a height of 1 meter, it would hit the surface in a microsecond, impacting with the force of a 1 kiloton atomic bomb. You could not stand on a neutron star. You would be instantly flattened into a 1-atom-thick layer of plasma, smeared across its surface. The gravity is so strong it bends space-time. A mountain on the surface of a neutron star is estimated to be at most 5 millimeters tall. Any higher, and the gravity would crush it back down. Light itself is bent. If you stood on the surface, you could see behind your own head. This is where the zombie analogy becomes real. The original star was spinning. As it collapsed from millions of miles wide down to just 12, it conserved its angular momentum. Think of an ice skater pulling in their arms. The star did the same. The result is a city-sized object spinning at incredible, violent speeds. We have found them spinning 600 times per second. An object with 1.5 times the mass of the Sun, spinning faster than a kitchen blender. This rotation turns the star into a lighthouse. It has powerful magnetic fields that channel beams of radiation from its poles. As it spins, these beams sweep across the galaxy. If one of these beams happens to cross Earth, our radio telescopes hear a pulse. Pulse, pulse. This is a pulsar. It is the heartbeat of the corpse. It is the proof that these objects are real. We have examined the outside. Now, it is time to cut it open. We begin our incision. The autopsy of a neutron star is a journey into a realm where our laws of physics are pushed to their breaking point. The atmosphere is a thin, hot layer of plasma, only a few inches thick. We cut through it. We immediately hit the outer crust. It is 1 mile deep. The gravity here is so immense that matter crystallizes. This is not rock. This is a solid lattice of iron nuclei trapped in a sea of electrons. It is the strongest, most perfect solid in the universe. But as we push deeper, things start to get weird. We are now in the inner crust, about 1.5 miles thick. The pressure here is so colossal that the iron nuclei cannot survive. They are crushed and they melt. The electrons have been squeezed into the protons, so the matter is now a dense soup of neutrons, with a few protons and electrons mixed in. These particles are at war. The protons, all positively charged, are trying to repel each other, the Coulomb force. But all the particles at this close range are being pulled together by the strong nuclear force. To find the lowest energy state, to find peace, the matter reorganizes itself. It creates nuclear pasta. This is not a metaphor. This is the literal, technical term astrophysicists use. At the top of the inner crust, the matter arranges itself into small sphere-like clusters of nuclei. Physicists call this the gnocchi phase. As we push deeper, the pressure increases. The gnocchi are squeezed together until they fuse, forming long, complex strings of matter. This is the spaghetti phase. We go deeper. The pressure is now unthinkable. The spaghetti strings are forced together side by side, forming vast, flat sheets of ultra-dense matter. This is the lasagna phase. And it gets stranger. Push deeper still, and the lasagna sheets are squeezed so hard that they connect, forming a solid, uniform block of nuclear matter, but with long, cylindrical holes or tunnels running through it. This is called the anti-spaghetti, or Buccini phase. Finally, at the very bottom of the crust, these tunnels break apart into isolated, empty spherical bubbles in a sea of solid nuclear matter. This is the anti-gnocchi, or Swiss cheese phase. This nuclear pasta is the strongest material in the known universe. It is 10 billion times stronger than steel. To break a 1-inch thick strand of this nuclear pasta, you would need to exert a force that no material on Earth could ever generate. This crust is, for all intents and purposes, indestructible. Finally, we reach the core. Here, the pasta dissolves. We are in a bizarre, superfluid, superconducting ocean of pure neutrons, with a possible unknown center of strange quark matter. We have reached the heart of the specimen. It is a stable, dead, spinning ball of the universe's weirdest physics. Or is it? Our autopsy seems complete, but we missed something. We missed the 1 in 10 chance. We missed the parasite.
About 1 in 10 neutron stars is not born this way. It is born different. It undergoes the same collapse, the same autopsy. But inside its core, a second process, a hyperdynamo, spins up. In the first few seconds of its life, this newborn neutron star generates a magnetic field of truly monstrous power. This is a magnetar. Let's put this in perspective. The Earth's magnetic field, which guides our compasses, is about 0.5 Gauss, a refrigerator magnet, 100 Gauss, a high-end MRI machine which can rip a steel oxygen tank from across a room, 30,000 Gauss. The average neutron star, or pulsar, about 1 trillion Gauss, already terrifying. The magnetar is 1,000 times stronger than that. Its field strength is measured at 1 quadrillion Gauss. That is a 1 followed by 15 zeros. This number is so large it ceases to be physics and becomes a force of pure Lovecraftian horror. This is not a zombie. This is a demon. Let's describe its kill zone. If you are 100,000 miles away from a magnetar, your body would be ripped apart atom by atom. The magnetic field is so strong it would overwhelm the electric bonds that hold your molecules together. You would dissolve into a cloud of atoms. At this distance, the magnetar would also wipe the data from every single credit card on Earth. If you were 1,000 miles away, a distance where you could theoretically orbit a normal neutron star, the magnetar's field would distort your atoms. The electron shells would be squeezed into thin, cigar-like shapes. The very laws of chemistry would cease to apply to you. You would be dead on a level that we don't even have a word for.
This is the true danger. A black hole is passive. A neutron star is predictable. A magnetar is unstable. Its magnetic field is so powerful, it is constantly twisting and stressing the solid, indestructible crust. The nuclear pasta we just autopsied is under constant, unbearable strain. The magnetic field lines twist and snap, and eventually the crust cracks. This is a starquake. When this happens, the magnetar unleashes a blast of gamma rays and energy that is, without exaggeration, beyond all comprehension. We have witnessed this. Case file SGR 180620, December 27th, 2004. On that day, a burst of high-energy gamma rays hit the Earth. It came from a magnetar 50,000 light-years away, on the other side of our galaxy. The blast was so powerful, it blinded every space-based sensor. It saturated them. It physically compressed and ionized Earth's upper atmosphere, altering our ionosphere. And it did this from 50,000 light-years away. The analysis was chilling. In 1/10 of a second, that magnetar released more energy than our sun will emit in 300,000 years. Think about that. 1/10 of 1 second. It was the single most powerful event ever recorded by humanity. Now, let's ask the final question. What if that happened nearby? What if there was a magnetar not 50,000 light-years away, but 30 light-years away? It wouldn't just blind our satellites. The gamma rays would hit our atmosphere and burn it. It would shred the ozone layer, exposing the entire surface of the planet to lethal cosmic radiation. It would cause a mass extinction event from a star 180 trillion miles away. The autopsy is complete. The neutron star is a masterpiece of physics, a monument to the forces of the universe. It is the perfect corpse. But the magnetar is the universe's ultimate warning. Black holes are the vacuum cleaners of the cosmos. They are frightening because of what they take. But magnetars, they are the attack dogs. They are frightening because of what they unleash. They are the deadliest objects in the universe, not because they can swallow you, but because they can reach out across the void with invisible magnetic claws and blasts of gamma-ray fire and end a world before it ever sees them coming.